Like all of our other three speakers today, Vijay needs no introduction. He's been on the OCP stage multiple times. He is responsible for driving the strategy for infrastructure technology at Facebook. Today, he's going to talk about some exciting new collaboration. Please join me in welcoming Vijay.
Thank you. Good morning. Well, great crowd. Thank you so much for coming in today. I'm super excited to share a bunch of new projects that we've been working on. We've got a lot to cover today, so I'm going to dig right in. At Facebook, we are responsible for growing and supporting 4 large communities. And these communities drive a ton of traffic. Billions of messages sent per day, millions of live broadcasts, resulting in significant increase in video and AI workloads. Let's focus on these 2 main workloads for today, video and AI. Our interest with video is closely intertwined with the mission of Facebook, which is to give people the power to build the community together and bring the world closer. These are just a few channels that our products use to communicate with our people. Our vision for video on Facebook is an experience where watching video is social and also interactive. We want to empower people to become active participants in the stories while also engaging with the content creators and the other viewers. Here's an example of how we are enabling video to be social via Facebook Watch.
This is the true story
of 7 strangers
picked to live in a house
to find out what happens
when people stop being polite
and start getting real. I'm transgender. It's been tough for me.
How many times have you been stopped and spread against the police car, honey? How many times?
You have AIDS, not HIV?
I have AIDS.
Holy, this is really happening right now.
No idea what I'm getting into, but I am so excited.
Hopefully, y'all are excited too. We know what we are going to get into. So let's start with some of the stats for our video. I'm going to just hold this slide up for a second, just to give you a sense of scale of the amount of video content we are getting in every single day and processing. Now, let's look at a few experiences and capabilities enabled by AI at Facebook. Hundreds of thousands of active bots are currently on Facebook Messenger and all powered by AI. On the Watch tab, we use AI to automatically generate previews so that you can actually get to see which videos you want to watch. AI is also a critical component in empowering AR and VR. We are not clairvoyant. We don't claim to be so. But AI enables our servers to make a non-trivial number of predictions every day. We train our models with more than 3.5 billion images. Training with this much data on a single machine would take us roughly a year, hence the need to scale out. At Facebook, we use AI to enable more than 6 billion translations every day. This allows people to communicate in the language of their choice. Training our models on such a large collection of data, images, and hashtags improves the accuracy and also enables much more fine-grained classification. As you can see here, from something as general to specifically calling out what that image is. Here's another case. We announced the use of neural network-based translation systems. This produces a much more natural and accurate translation compared to phrase-based systems. Those who are familiar with Hindi, I'm sure, would appreciate what you see here. We are now capable of serving translations in more than 4,000 language directions. Spanish to English is an example of a language direction. Here's another large-scale problem that Facebook decided that we needed to use AI to help solve. Countries all over the world are facing a blood shortage. So we saw the need to actually launch blood donations on Facebook. This helps connect people, blood banks, and hospitals to donors. Today, this is a feature in India, Bangladesh, and Pakistan, with many more countries on the horizon. We want to share how we are using AI to help connect people in this aspect. When people post their need on our systems, our AI systems then will help the users take their posts into a public post and then send the right information appropriately. Our AI systems take inputs like blood type, location, and then notify the users with a similar blood type who have enabled location and who are in the vicinity. Instantly, this connects the right people with the right posts in a situation where every single minute counts. AI has been a key driver in developing products like the ones we just talked about. However, now let's take a look at how the industry is tackling these challenges. Solutions to many challenges can be found by examining history. I'm going to pause here. How many people remember the 8087? Excellent. I'm glad not too many shy people here. Excellent. 2 years is 2 years good. The above quote is from Wikipedia. Thank you for documenting history. Now let's look at the similarities with what we need from the inference accelerators today. The focus is more on integer math. However, specifically matrix multiply and accumulate. However, the objectives are the same. Now let's look at another similarity. When engineers design a service, they typically are making trade-offs between 4 basic elements: compute, storage, memory, and network. Accelerators are a new component that are purpose-built for a given application, and that has joined this group. Now, let's look inside an inference accelerator, and you'll see the similarities again. Much like a data center, engineers now make trade-offs around sizing compute, memory, and buffers. A new resource that was added is GEMS, which is general matrix multiplication. And the layout of this chip determines the network bandwidth that you've got between these resources. However, unlike data centers, where the ratios between these resources are reasonably flexible, there is absolutely no flexibility once this chip is in production. So it's key to understand what the ratios would be before we design this chip. At Facebook, we are investing heavily in the advancement and development of purpose-built hardware. We've been doing this for a long time now within the open community through OCP. Today, we are adding another dimension with custom accelerators. We've been working with a number of partners, and many of them are going to be listed here today. Let's look at some of the system-level solutions that incorporate these accelerators. Yosemite was a platform we introduced a few years ago. Today, we show how it can be tricked out with accelerators. Twin Lake is the compute card that a lot of us are familiar with. Glacier Point, that is our storage as well as accelerator card. It houses a number of M.2-based accelerator modules. This allows for a good balance across compute, memory, and connectivity. It also fits into the same Twin Lake slot and can replace a compute card. The compute host then connects to these accelerators via PCIe. Putting it all together, each M.2 module houses the ASICs, its memory, and the associated circuitry. The carrier card houses multiple modules and provides flexibility. The carrier card then couples with a twin lake in a Yosemite chassis. Please visit our booth for more details. As you saw earlier, we are seeing an increasing demand in video usage across our products. So we needed a purpose-built accelerator to tackle this. Facebook's video applications range from live video, which has a very different set of characteristics from video-on-demand products like Facebook Watch. We need a flexible ASIC design that can encode a large number of streams at a lower bit rate for live video, but can also trade off throughput with higher quality for products like Facebook Watch. And here are a few partners working closely with us on designing this ASIC. We definitely encourage more partners to work closely together in tackling this challenge. Switching gears. At its core, inference is the act of looking up or recognizing an answer. This is very compute-intensive, and it lends itself very well to accelerators. Given the growth of AI at Facebook, it became imperative for us to accelerate inference too. Here are some specs that we'd like to share with the industry. We would like the industry to target at least 5 teraops per watt. The bar is high, but it's definitely achievable. For those who are curious, including the person who is 2 years old, 39 years ago, the 8087 could perform about 50,000 flops using 2.4 watts. SRAM, DRAM, PCIe bandwidth, these are all additional factors to consider while designing this ASIC. We've been working closely with a number of partners on designing ASICs targeting inference. Again, we encourage more partners in the industry, because this is a growing problem, to work together in tackling this challenge. The throughput increase of running inference on an accelerator compared to a traditional CPU needs to be worthwhile. In our gauge, it should be roughly 10x on a watts or a TCO basis. To achieve this, the software needs to be co-designed with the hardware. Glow is our compiler for AI workloads. So we recognize the need for new tools to enable hardware acceleration. An open ecosystem and interoperability are key characteristics for any accelerator to become widely adopted. Glow has already been open sourced. It's on GitHub. We recognized very quickly how Facebook could contribute. We are lucky that we have a number of really cool compiler engineers who worked on HHVM, so this came pretty naturally for us. Glow features a powerful optimizer, quantizer, and code generator. It compiles an AI graph into low-level instructions. Again, we are very happy to announce multiple companies have committed to working with Glow and supporting the software system. We've always favored a community-based approach rather than going all alone. Let that sink in. That's what an AI model thinks. It's got data. All jokes aside, AI training is the act of building a model based on already available data. It's a completely different beast compared to inference. And networks for AI have a long history, and they've been evolving over time. In recent years, sparse neural networks is one amongst a number of neural networks that have become very popular at Facebook and some of our peers. Upcoming networks pose a unique set of challenges. Let's take a look at some of those. Upcoming neural networks are a combination of large embeddings and a reasonably sized set of matrix multiplications. Unlike CNN and LSTM, upcoming neural networks have a large memory footprint, sometimes up to 2 terabytes. This makes them memory bandwidth intensive as well as capacity intensive. Processing sparse features results in big embedding tables, and then this results in many irregular accesses into large chunks of memory. You can hear me say accesses, large memory. That's because capacity and bandwidth are our two key problems. Majority of the compute is from the MLP or multi-level perceptron layer. This translates into tall, skinny gems. And the lookups and executions are done in parallel. These result in an all-to-all communication. The current trend that we observe is rapidly increasing model size, but slower growth and activations. Now let's take a look at a system designed specifically for training. We set out to build a system with industry standards as building blocks. So we designed an 8-socket CPU-based system called Angel's Landing. This was to target the memory-intensive portion of the problem. It uses standard DRAM, which is readily available at a more reasonable price compared to HBM, high bandwidth memory. The memory channels are spread across 8 sockets, providing large memory capacity and large memory bandwidth too. We disaggregated the compute, or the accelerator portion, into its own subsystem. That's named Emerald Pools. This is based on a common module form factor. We worked closely with the community. Yes, that project was called Common Module Form Factor, and then finally it got a new name. This system is flexible to incorporate multiple types of interconnect, ensuring a high bandwidth path for the all-to-all step that we talked about. The common module form factor is capable of housing GPUs and accelerators dedicated to training. We are very excited, and with the support and the engagement that we had with the community on standardizing this design. I have something to show you. Whitney from our team has been the key driver and person who collaborated with the industry in driving everyone to this standard design. I'm going to hold this up here for a few seconds so that the cameras can zoom in well. Please check our booth. Yes, I'm not a model, so I'm going to keep it far away from me. Please check our booth, and also Whitney's talk for more details. Yeah, that's about how steady I can be. OK. Here are some of the companies supporting and engaging with the community on standardizing this common module form factor. It's called the OCP Accelerator Module, or OAM. You heard Microsoft talk about it too. This is a shining example of the true power of OCP. Bill will be providing more details about this project soon after my talk. These two subsystems are then connected via standard PCIe, forming a tightly coupled system named Xeon. Xeon is optimized for training the most demanding neural networks, either for high memory, high compute, or high connectivity. These systems are very modular, and so they could be subdivided if the application so chooses it. Also, this design can scale out further by deploying multiple systems in a rack connected to each other, again, with industry standard components. That was one of our key deciding factors. Wrapping things up, silicon is hot again. Designing scale-out systems with accelerators in mind is a key challenge a lot of people in the industry need to look out for. But this is also an opportunity. The industry is already moving fast in this direction. As a community, we need to remember to be open with these challenges that we are facing so that we can solve them collectively. Thank you.